Okay, so part two. So we basically did this up here. We did the light reaction, right? And the whole purpose of the light reaction is to make the energy ATP and NADPH, the electron carrier. And it's like, okay, now what do we do? We're gonna do part two. Okay. Now part two has a couple different names. It used to be called the dark reaction because it didn't like the other one used light. So okay, let's call this the dark. And then we realized, well, it can't it's not really something that happens in the dark because you can't keep this cycle going without ATP and NADPH, which needs the sunlight. So then they're like, okay, how about we call it if we have the light dependent, let's do the light independent. But these two cycles, these two phases are completely dependent on each other. So that didn't work, right? So then we called it after the person who discovered it, which is the Calvin cycle. Okay. And with the Calvin cycle, what's happening here is this is should look very, very similar to the Krebs cycle, except for on the Krebs cycle, we were pulling or harvesting hydrogen off of sugar. Remember, I said this is backwards. So in this case, we're going to be taking the hydrogen and putting it back on CO2, right? And now it gives our CHO, carbon, hydrogen, oxygen, which is what we need for sugar. So we're going to start by taking RUBP, which is a 1, 2, 3, 4, 5 carbon molecule. We're going to add a 1 carbon molecule, and they should have actually, whew, there's a 6 carbon molecule here, but it's so short-lived and split in half. And that's going to give us this molecule here, which is called PGA, which is short for phosphoglycerate. And then we're going to take our ATP. Notice there's one phosphate here. Let me do that in a different color. There's one phosphate here. I'm going to do it in a different color too. Let me do it in yellow since ATP is yellow. One phosphate here. We put in phosphate. Now we have two. Then we're going to put in our hydrogen. All right. We're also going to notice we have phosphates coming out. And then we have G3P, which is important. G3P is your molecule that is used to make all your biological macromolecules. All right, and then we're going to take what's left of our G3P and move it through. We do need to energize it or put phosphates back on, right? So that we have our UBP back. The important thing is, and let me see if I can do this. Okay. The important thing is balancing this. And I don't know how important it is to actually balance this. But if we have three, oh, I was hoping that would get rid of it all. Yeah. Let me see if I move on. Oh, okay. We have three carbons here. We have three RUBP. So if you think about it, it's 1, 2, 3, 4, 5. That gives me 15. 15 carbons. I'm putting in three, so that gives me 3 carbons. And then our intermediate molecule here has 18 carbons. And then we're just going to split those in half. And notice we have 18 PGA, or 18 carbons in 3 PGA molecules. All right. Now we're going to put in those ATP, the energy from those electrons we took off water. And now we have G3P. G3P is going to exit. And then we're going to put in a little bit more ATP. So let me balance this now. So we have 3 times, we have 3 of these, we have 5. So 3 times 5, 15 carbons. 3 carbons. That's 15 plus 3, that gives us 18, right? That's what we have here, 18 carbons. 18 carbons. We are going to get rid of one G3P, so we subtract 3 carbons. Here, notice we have 15 carbons back, and then we're back to 15 carbons. So we're putting in 3. We're putting in 3 carbon atoms, and CO2 is considered inorganic. And we're pulling out 3 carbons that are now organic. Remember when we talked about organic versus inorganic? Inorganic does not have carbon and hydrogen. So CO2 is inorganic. Um, Organic contains carbon and hydrogen. So we are what we call fixing. We're fixing carbon here. It's coming in as, I mean, you can think of it as broke because it's inorganic. And then we're throwing those hydrogen atoms on there that we picked up from water to fix it into an organic molecule. And then you can see here, this is where we're going to make glucose. So we need 2 of those G3Ps to make glucose. We can make our lipids. We can make amino acids. All those lovely little things that we need for plants to provide those molecules to live, right? They don't eat their food. All they do is get sunlight, water, and CO2, and they're able to turn that molecule into, I want to go back, um, into an organic substance. Now, I like to do 4 phases. Now, the first phase here is what we refer to as carbon fixation. The second one here is energizing the sugar. Exit of product. And the last one is regeneration of RUBP. Okay. The fate of G3P. Remember, that's our product we just made. We can make sugar. We can make fatty acids. And we can make amino acids. All right. So remember with glucose, glucose is starch. We can store it as starch, or we can use that as cell wall formation. So lots of different things here. All right. Now, we do have a problem called photorespiration. If you think about it, we talked about photosynthesis and we talked about cellular respiration. Hey, let's put them together. Okay, so green is good, yellow is bad. All right, so we just followed the Calvin cycle, right? We put in ATP, we put in our NADPH, and we got out what we want to. Yay, we got sugar. And again, that sugar is now going to go to the mitochondria where it's going to happily take it back apart and produce a ton of ATPs, right? So Rubisco is important. Rubisco is where we're going to fix that CO2. So CO2 gets taken in and held by Rubisco and put together with RUBP to make our PGA. Problem is, plants were around before free oxygen. And so it didn't matter that Rubisco's binding pocket was, I don't want to say it's a little loose, but it allows for oxygen to bind to it as well. So you could call oxygen a competitive inhibitor here. So what happens is when Rubisco grabs oxygen instead of CO2, right? We take in oxygen for respiration. It is going to notice we're using our products from the light reaction, ATP and NADPH. It's going to kick out CO2 and it's going to use some more ATP. We don't get sugar. We do not get the sugar. So it's using all that energy that we just spent time making in the light reaction to do basically nothing. It's unproductive, right? So some plants have formed adaptations to cope with this photorespiration. All right, so that's C4 and Cam. Now I want to go back. Come on, back, back. Wow, that's a mess. Okay, I'm just gonna leave it like that. Notice three carbons, three carbons, three carbons. So besides the Calvin cycle, this is also called the C3 cycle because everything is three carbons. So this one is considered C4 because what happens is it's going to use a four carbon compound to store CO2. So in these really hot places where we're going to lose a lot of water, remember you have, oh, that's not good. Let me do this differently. Let me draw this better. You have those two guard cells, and those two guard cells make that pore that we have CO2 going in, and we have oxygen going out. We do not want to lose water vapor. Plants need water. We don't want to lose water. All right. So what happens is for those guard cells to be nice and erect, full, for those pores to be open, that central vacuole is full of water, putting turgor pressure on those cells. When we lose water, those cells go flaccid. They droop. And so this is open, and it closes the stomata. The stomata is the opening. The stoma is closed. So we don't want to lose water vapor. The problem with this, and this is where these plants, usually in the hottest part of the day when they're losing water, they'll close up shop. Okay, and then once the water vapor is kind of replenished as it's getting colder, right? Because the plant is constantly taking water up through the roots, they'll open back up again. But while we're closed, we have stored CO2 in this four carbon compound so that the carbon dioxide can still get put into photosynthesis and prevent photorespiration. So it's keeping the store open even though the front doors are closed, we can say the shop is closed, but we're still doing internet business. Okay? So we're still making sugar. Now, there is another mechanism or adaptation that some plants do use when they're in really kind of, I don't want to say hostile climates. Pineapple's one. We also have cacti use CAM. What that is that you can see here, nighttime is the only time it's open for business. At night, the stomata open and it stores up that CO2 in that four compound molecule. And then during the day, when we have plenty of sunlight, the stomata close, but we have stored CO2 to make sugar. Generally, these plants do not grow very fast. If you've ever had a cacti, you know it grows very slowly. All right. So, yes, we have modified our system to prevent water loss, but there are going to be some consequences to it, and generally that is a grow slower. And to talk a little bit about the greenhouse effect, because we know plants are so important with producing oxygen. Since plants are taking in and CO2 is a greenhouse gas, plants help to reduce the number of greenhouse gases that we have with that CO2. What the greenhouse effect is that as the sun is sending its waves to our planet, the atmosphere, the clouds, the surface reflects that energy back out into space. Okay? Now, with the greenhouse gases being up there, what happens is, this one was trying to leave, and the greenhouse gases act kind of like a blanket and prevent them from leaving. And so it starts to heat up our planet, our overall planet temperature. Plants are so important for using that greenhouse gas to help maintain the level of CO2 we have in our atmosphere. And as you know, we are cutting down the rainforest, which is almost like the lungs. Everybody talked about the rainforest being the lungs of our planet. And yeah, they are. They are important. They're basically kind of like our number two set of lungs. Our number one lungs for our planet would be plankton, phytoplankton in the oceans. And as you guys know, our oceans are getting heavily polluted. And so that's not helping either. And so between the pollution in our oceans and cutting down the terrestrial plants, you could say, versus the aqueous, our CO2 levels are climbing, and it has contributed to climate change on our planet. So just a little push there for our ecology. Okay. There is a video here that you could watch. It talks about it. I would highly suggest doing that on your own time. But another important thing is ozone. So ozone is made with oxygen. Of course, we didn't have free oxygen, meaning there was no oxygen molecules in the atmosphere until plants. Plants through photosynthesis release this gas. The oxygen goes up high in the atmosphere where the sun rays do some chemistry. And that chemistry is important because it creates ozone. Ozone is O3. I know if we were just to talk about octet and all that, you'd be like, how the heck do you have three oxygens? But this is what we call a resonance structure. And you'll learn more about that in chemistry. Right? But either way, it's so important because it absorbs UV light. This process uses that UV light to keep that reaction going, and it decreases the amount of UV light going to the surface of our planet. This decrease in UV light was what allowed for life to exit the water and go on land. As we know today, we are putting the family, the halogens, which is specifically chlorine and bromine, up into the atmosphere. And remember, they're highly electronegative, and it is completely interfering with this process. It is decreasing our ozone production. And many of these molecules that we put up there have a half-life of like 50 to 100 years, meaning that in 50 years, half of it will be gone, or 100 years. And so many of the manufacturing processes that were releasing these hydrocarbons up into or chlorofluorhydrocarbons up into the atmosphere, um, we have worked really hard to reduce that. Styrofoam today is not the same styrofoam that was when I grew up. The styrofoam today is much more expensive to make, which is why many of our food products come now in cardboard, your fast food stuff. You also have refrigerants that had to be changed and aerosols. So we have gone through a lot of effort to help clean up our planet, although not all countries are following this. And this is a global effort that has to happen. It's not like we're going to just replace the ozone over the United States, right? This is a global issue. So when they start talking about, all these other countries dumping stuff into the atmosphere, you need to be concerned. Okay. So the question is, they were hoping that the ozone layer was going to get better. We know we have a big hole in the ozone down and around Antarctica, and you can see that in the blue. Okay. And you can kind of see where it gets smaller, like 2002 is smaller. The dark blue, we don't want the dark blue. All right, so the dark blue is bad, and then it got bad again, and then it gets better, and then it gets bad. And so the question is this due to countries not following protocol, or is this a natural waxing and waning that happens with our planet because we really didn't have this technology, prior to, late I think it was like the late 90s or so. So we really don't have a very big sample size yet, all right, to know is this natural or is it, again, our influence on our planet. So it's just something I want you to be aware of because it is important. I know that like me particularly, I teaching ecology is like my least favorite thing, but it is the most important thing you could learn about in science. All right. It is the one that's going to impact you in your life more than any other topics, whether it's anatomy and physiology. Yeah, you might be a doctor or a nurse or whatever, but having air to breathe, you kind of need. So, very, very important. So, you can now relate photosynthesis on to how plants have influenced life on our planet and what we're doing with cutting down all these plants, covering places with concrete, and how that's affecting our planet as a whole. We all need to do our part with keeping our planet healthy. All right. I'm going to get off my soapbox now and you can go back through. I would highly suggest doing the same thing you did with cell rest, kind of write it down, talk out loud as you're writing it down. It helps you to process things kinesthetically, that's writing, and visually because you're looking at it, and then auditory. So you're using all three senses to try to retain this information. All right, have any questions? Again, write them down and bring them to class. Thanks for watching.